Hi, my name is Colin Frosch. I'm a civil engineering student at West Virginia University in Morgantown, and I'm studying transportation engineering as part of civil engineering. I created the traffic control part of the peer presentation, and right now in college I'm doing some research with a civil undergraduate professor looking at how we can make roads more efficient, how projects in the past, how they could be improved in the future. One of the things I'm really interested in is designing roadways. I like roundabouts and new different types of intersections. While I'm here at WVU, I've been a part of many different organizations, including Engineers Without Borders, where we were able to take a trip to Fiji and help a small village get clean water by creating water filters for them. I'm also an ambassador here for the College of Engineering, so I do things like this where I am able to go out to other schools, to elementary schools, high schools, and teach kids about engineering, teach them about careers that they can have in engineering and STEM related fields. In the future, I hope to work for a consulting firm doing transportation related work in the civil engineering industry. And this summer, I currently have an internship position in Austin, Texas, where I'll be working with a company doing transportation engineering related work. I really got started with engineering when I was young. I liked learning how things worked. I liked building things with friends, with family, toys and Legos and things like that. Also just using wood and scrap pieces I could find around the house. I like trying to figure out how things worked and trying to build new things and design things that would solve problems. And at civil engineering, I found a good fit because I liked helping as many people as I could. And so civil engineers, what we do is we build things and we construct things. We design structures that are going to help the entire society, not just one group of people that can afford some great new technology, but we're building buildings and bridges and intersections and all these different transportation systems that can help the entire society, so we can have a better economy, that people can have a safer environment around their homes and their workplaces. And all these things are things that people need on a day-to-day basis. Today we're going to be talking about traffic flow characteristics, kind of get a feel of what makes up transportation traffic flow, talk about signal analysis, safety, and intersection types, so we can get a good idea of how engineers try to control the transportation environment around us. And all of this is going to be within the context of roadways, so highway usage. So we're going to start by talking about what are some of these different vocabulary that we use to describe traffic around our area. So we're going to start with density, which is the number of vehicles that are traveling on a mile of highway at one time. So as you can see here, the units are vehicles per mile. And then on the other hand, we have volume, which is the number of vehicles that we have passing a certain point in a certain amount of time. So most of the time we're going to say these are the amount of vehicles per hour. So when you're looking at this at a particular type of road, you can ask, well, why is this road congested? What is contributing to this road's congestion? And these two things are all because of the capacity. So what do you think controls the capacity? It is the volume and density, because a certain road can only hold a certain amount of vehicles per hour and per mile. So when that roadway starts to exceed or approach that capacity for the volume or density, that's when you're going to have a congested roadway. So if you look at this picture right here, which lane do you think has the higher density and which lane do you think has the higher volume? So let's just assume that this lane over here on the left side is traveling near standstill speed, so not moving, and you can see that the cars are really close together. On this right side, the cars are traveling a lot faster and there's space between them. So if we just took a snapshot of this picture, which one do you think has the higher density and the higher volume? So when we look at this, you can tell that this one has the higher density, because when we took our picture, you can count there's nearly 100 vehicles just in that one stretch of a mile. On the other hand, this lane, the right side, has a higher volume because there's more cars traveling through in 1 hour. We can say probably 100 or 200 cars are traveling past this one point in only an hour. Whereas this lane, because there are so many cars but only traveling at a minimal speed, there's going to be very few cars passing, say, this point at a single given point in time. So now we're going to talk about waves. Maybe something you've never thought of in the transportation sense may be more of in going to the beach or going to a wave park. But we actually do have waves in transportation engineering, and it's basically caused by changes in volume and density in a roadway over time. So now when we look at this video, it's going to explain to us and show us a visual representation of how traffic waves are present in a traffic engineering situation. You can imagine it's kind of like a pebble dropped into a pond. It causes a ripple effect. So when the volume and the density change, you're creating a wave. Here you can see there's a relationship between the speed and the density. And we call that the flow. Because the flow is the volume over an hour of time. So it's kind of like the volume, how many cars are passing a specific point in an hour of time. But you can see there's a linear relationship between the speed and the density. You can imagine when the speed is really low, you're going to have a really high density because the cars are bumper to bumper. When there's very high density, the speed is really low, and when the density is really low, the speed is really high. It's kind of like if you're driving down an empty interstate, you're going to be able to go the full speed limit because there's no one else there interacting with you, contributing to how fast you can or cannot go. And when we look at the relationship between density and flow and speed, you can see they make a parabolic curve. On one side of the parabola, you can see that flow is uncongested, or on the other side, it's a congested flow. Because once the density gets up to a certain point, or in this case, once the speed gets up to a certain point, then the flow starts to decrease instead of increase because the cars are getting too close, packed together, means they have to slow down. They can't go as fast as they would hope to do. So that's the end of the first section. Now we're going to move on to signal analysis. This is more than just looking at red lights and green lights and deciding what are the three colors we're going to use and where are we going to put stoplights. There's a lot of engineering thought and management that goes into the establishment of these traffic lights. So first we have to know some different vocabulary about these. We're going to start with cycle, which is the time it takes so that every light on a single intersection gets the green light once. Whereas the phase is a group of lights that have a green light at the same time. So if you're in a regular intersection, traffic usually flows opposite directions at the same time. So both of those lights would have a green light, which would constitute a single phase. We can also draw what we call phase diagrams to depict the different motions of traffic at a single time. So we can plan out who's going to have different turns at different times, and we can make sure that there's going to be no interferences so that people aren't turning left when other people are trying to go straight. We also have two specific things specifically for left turns. We have a protected left turn and an unprotected left turn. So protected left turn means that there's no one that you have to look out for as you're turning left. If you can imagine when you come up to an intersection, when you have to turn left, you have to look for oncoming traffic. Well, if it's a protected left turn, you know that the oncoming traffic has a red light, so you don't need to wait for them or look for them. However, an unprotected left turn means that you do have to look for oncoming traffic. So in this case, an unprotected left turn would be a solid green light, whereas a protected left turn would be a green light with an arrow. And when we're doing our phase diagrams, we designate the unprotected left turn as a dotted line, whereas the protected left turn is a solid line. So right now we're going to look at an example of an intersection, and what I want you to do is take out a piece of paper and a pencil, and as you're watching the simulation of this intersection, try to create your own phase diagram. So draw lines for where you think the cars are going at different specific times, and be sure to look out for the protected left turns and the unprotected left turns. And remember which one's a dotted line and which one's a solid line. So watch that a couple times and see if you can come up with your own phase diagram. What you end up with is something that looks like this. Because at first you have the traffic is going through and turning left. As you can see, that's a protected left turn. In the second phase, the traffic's still going through that same direction, and then once we head on to phase 3 and phase 4, we start with the protected left turn for the traffic going, let's call that north-south. However, then in phase 4, that green turn arrow turns into just a regular green light, so they can still turn left, however, it's an unprotected left turn. If you want to watch the video again, go ahead back and watch again, see if you can follow the phase diagram throughout the video. So we also look at signal timing. How long does each light need to be green? How long does it need to be red? And while we're looking at that, we're trying to figure out how many cars are trying to use this intersection. How many of those cars are trying to turn left, go straight, turn right? We're looking at the demand for that intersection. So as you know, we have 3 different signal stages in every light. We have red, green, and amber. Amber is more commonly known as yellow. However, in transportation engineering, we refer to it as amber. And all red time is when all the signals at an intersection are red. Why do you think we would use something like that when every single light is red for maybe a second or two? Really, that's so that we can make sure the intersection is clear before we make another light green, so that the intersection, there's not going to be any added collisions. So for example, if you have cars coming through and their light turns red, if the light to go the other direction immediately turned green, if there was someone sneaking through at the last second, you could cause a collision. So instead, we err on the side of caution, add an extra second or two, so that every light is red, and then once the intersection is clear, the light can turn green again. This is what we call a signal timing plan. As you can see, we have 2 groups of lights, and when one group of lights is green, the other one obviously has to be yellow. And you can see here we have about 5 seconds of all red time, so that we can make sure that the intersection is perfectly clear before we start the next green phase for the second group. And of course, you have to allow some time for the amber so that people know that the red light is coming. So now let's look at this example of an intersection. You can see that this way, let's call this the east-west direction, has 2 lanes, one for a through and one for a left turn. And they have about 500 vehicles per hour, whereas the north-south direction has just 2 lanes, and each lane is used for every direction. So go ahead and take out a piece of paper and a pencil again and try to draw your own signal timing plan with a cycle of 120 seconds. So the maximum for your green time should probably be around 40 to 45 seconds. Now, however, you can increase that if you want to give one direction more time than the other, because as you can see, this direction has more vehicles per hour. So this is an example of one of the signal timing plans that you could have come up with. As you can see, the group 1 is a left turn lane. So for this first section here, we have a protected left turn for the first 20 seconds. That way, they have a protected left turn. They don't need to worry about oncoming traffic. For the next 40 or so seconds, they then have an unprotected left turn because there's through traffic coming through. We then have our amber phase, our all red phase, and then group 3, this is for the north-south traffic, so that they can get through too. And as you can notice, the east-west traffic has a longer green time. And as we noted earlier, that's because there's more traffic trying to come through in that time. So now let's going to talk about dilemma zones. Have you ever come to a traffic light and you or your parent is driving and the light turns yellow and you have to make, or amber rather, you have to make the decision whether you're going to go through the intersection or stop before the intersection. And that's a split-second decision they have to make. Sometimes you can't make the perfect decision. Sometimes you try to stop and you don't really are able to stop in time and you stop within the intersection. Sometimes you try to get through, but you can't get through in time before the light turns red. Thankfully, we have an all red phase, so you're not going to get into an accident most of the times. But this is something we call a dilemma zone, where you don't have enough time to get through the intersection and you don't have enough space to stop at the intersection. As you can see through this lovely animation. This is what you should do. You should be able to stop right when you get to the stop line. So in the first case, you don't have enough space to stop. The light turns amber, you decide to stop, but when you try to stop, you end up stopping in the middle of the intersection because of physics. Your car can't stop in time or in enough space. In the other case, you try to get through, but by the time you get through the intersection, the light's already red. So if someone was turning right or cutting through the intersection, you could get a ticket, you can get an accident. So both of these situations aren't ideal. So how do we decide whether someone's in a dilemma zone or not? First, we're going to look at the stopping distance. This is going to be calculated by taking the distance traveled during your decision multiplied by your time and speed. And then we're going to take the distance for your car to stop. So for example, if you have a big truck, it's going to take a lot longer for your car to stop, whereas if you have a small sports car, your car will most likely be able to stop sooner. On the other hand, how long is it going to take your car to get through? You take the distance to the opposite side of the intersection and divide it by your speed. This is assuming that you're keeping the same speed and you're not going to try to speed through the intersection. So if the space needed to stop and the time to get through are greater than your amber time and the available space, then you're in the dilemma zone. So let's look at an example. Bob here is driving 40 feet per second when the light turns amber and he's 100 feet away from the intersection. Should he try to get through or should he stop if the amber phase lasts 3 seconds? So we're going to assume that the intersection is 40 feet wide, his car is 20 feet long, and it takes him 1 second to decide to stop. And it takes his car 25 feet to stop for every 10 feet per second his car is traveling. So since his car is traveling 40 feet per second, that would mean his car would need 100 feet to stop. So take out a pencil and paper again and try to calculate whether he should stop before the intersection or continue through the intersection. What you should have gotten is that he's in the dilemma zone. If he tried to stop, it would take him 140 feet to stop, which would mean he would be in the middle of the intersection because it's greater than 100 feet. If he tried to go through the intersection, however, it would take him 4 seconds to get through, but he only has 3 seconds because that's how long the amber phase is. So Bob is in the dilemma zone. As transportation engineers, what we should try to do is try to get rid of these dilemma zones by reducing or increasing the speed limit, making amber phases longer, things like that, so that we can avoid having people in these dilemma zones. Now you can try to control your own signalized intersection. It's a short little game trying to control different intersections by changing light green and red, so you can kind of get an idea of what traffic engineers do when they're trying to plan out an entire city, entire grid of traffic lights. So now, let's look at this picture here. We're going to start talking about safety now. Break into small groups of 3 or 4 and make a list of what components of this roadway do you think were implemented in an engineering standpoint for safety. So some things that we can implement for safety include signs. Many of you have probably seen speed limit signs, chevron signs, caution signs. They're all things trying to inform drivers and alert them to oncoming traffic, new dangers up ahead. We have, caution for deer crossing, caution there's a tight right turn. We also have electronic display boards. You can probably see these on game days in university towns and big events, things like that, or if there's construction going on. So we can use these signs to inform the driver so they can make the best decisions and they don't have to be alarmed if they come across something. The next thing we do is lighting. Most of the time it's pretty inexpensive and it's actually the safest and the most safety increasing implement that we can add to roadways. As you can see here, you can see for almost a mile down this road without your headlights, and that can alert you to objects in the road or oncoming traffic that might have swerved into your lane way before your headlights would have gotten to them. So that's a big plus for safety, is adding lighting. It's also a lot easier to navigate, especially in rural areas where it's curvy roads and your headlights can't bend around the corner. Something else you might have seen is rumble strips. That's where we take little bits of the road out on the side or the shoulder of the road, so that if a driver would fall asleep or become distracted and they start to go off to the end of the road, the rumble strips, once they hit the tires, are going to make a loud noise and a vibration, so it would wake the driver up or alert them that they're coming off the road. Something new that we've been testing is something called rumble stripes. It's where we take a regular rumble strip and paint a second line over it. So it's kind of a second warning line. During the day, you can tell that it doesn't really make much of a difference. It just gives you a second white line. However, when you look at night, you can tell this is the same area. You can't really see the solid regular line. However, on the rumble stripe, you can. It's because the surface of the rumble strip gives you a vertical surface that you can paint on. So when your lights hit the paint, it's going to be reflected right back to your eyes. So that way, when you're driving at night, this is a lot easier to see. It'll help you keep calm as you're driving at night. We're also going to talk about speed control, something you might see in small neighborhoods, mall parking lots. We use things like speed bumps, where you're going to, if the car's going too fast, it'll make an aggressive bump. Most of the time, it'll alert drivers to keep them slow and so that they can keep going at a regular pace. We also use textured roadways, which is pretty much like taking a rumble strip and creating it across the entire road. As engineers, we try to make the roads forgiving. We don't want to make a road that if you make a simple mistake that you're going to get injured or have a lot of money to go to fixing your car because it was highly damaged. So we try to make these roads forgiving. What we mean by that is if you make a mistake, it's not going to be the end of the world. For example, we have wide shoulders here. So if someone fell asleep when they're driving down this country road, they're not going to go off the road, hit a telephone pole, and ruin their car, have to be sent to the hospital, something of that nature. Instead, they have 4, 5, 6 feet of space that if they come off the road, they can have enough time to control their car and get it back on the road with a lot of safety in mind. We're also going to talk about guardrails. A lot of times these can be used for protecting you from falling off a cliff, or in this case, protecting you from going into someone's yard. A lot of times guardrails are designed actually to break and to crumble. So in the case of this one, what it would do is it would slow you down by increasing the amount of time you're impacting the guardrail. If this guardrail was made of solid concrete, you would hit it and have a really hard impact. But because it's soft, made out of timber, and specifically designed to break, it's actually going to slow you down so there's not a lot of damage to the car. Now, if it was a guardrail on the side of a cliff, however, then of course they would make it sturdier so that you don't fall off the cliff. The third thing we have is called a safety edge. Instead of having the edge of the roadway perfectly perpendicular to the roadway, what we do is we make sort of a slant to the road. So if your 2 outside tires come off the roadway for even a little bit of time, what you can do is you can regain control and get your car back on the road without having to come into an unsafe situation. Whereas if the road was completely perpendicular right here, you wouldn't be able to get your tires back up onto the roadway. So that causes crashes, and that's actually one of the leading causes of accidents is people fall off the road for a little bit and aren't able to get back on. So now that we talked about different aspects of safety that we can implement as engineers, take out your piece of paper again and look at this picture. And we already went through and described what they already have in this environment to create a safe driving atmosphere. But now what do you think they could add? Could they add some more lights, some rumble strips, a rumble stripe? Make a list of some things they could add, or some things that they could change about the road to make it safer. Our last topic is intersection types. First, we're just going to look at a conflict point diagram where we're going to trace the different routes of every vehicle traveling through this intersection. And then we're going to color code every time that the lines either cross, diverge, or converge. And these show different conflict points, so places that people can get in accidents. For example, a crossing point is where you would have a T-bone collision or a head-on collision, something of that nature. Diverging and converging, however, would more be like side swipes, bumper-to-bumper collisions, things of that nature. So, as you can see, this is just a regular 4-way stop or a 4-way signalized intersection, and it has a lot of conflict points, 32 to be exact. So what we try to do as engineers is try to decrease the amount of conflict points. So what we're going to do is design different types of intersections so that we can, like I said, decrease this amount of conflict points. One of the more up and coming and more widely used nowadays is a method of intersection called a roundabout. Basically, every car entering this intersection has the same opportunity to use the intersection. There's no stop signs, no one has higher priority going one direction than the other, and there's no stoplights. So when you approach the roundabout, there's a yield sign. You must yield to anyone that's in the roundabout already, which consists of this circular area. And everyone has to move to the counterclockwise direction, so to the right. Once you enter the roundabout, you basically proceed until you get to your exit. So if you wanted to go straight in this intersection, you would enter here, wait for the roundabout to be clear, proceed around, and then exit the roundabout whenever you get to your exit or to your leg of the roundabout. So this turns all the movements into right turns. The entering traffic is yielding, it keeps traffic moving, and it slows people down because you can't go around this tight circle at 50 miles per hour. You're going to have to reduce your speed to probably half that, 25 miles per hour. So once you approach it, you slow down. It makes a much safer environment. As you can see here, there's some pedestrian crossings around the outside of the intersection. If this was a signalized intersection, you wouldn't feel as safe as a pedestrian to cross a road if the speed limit's 50 miles per hour per se. But in this case, because the traffic is alert, they're slowing down to enter the roundabout, you feel safer to be able to cross the road in this case. So let's go ahead and take out your pencil and paper again and try and draw a conflict point diagram for a roundabout. And then we're going to compare that to the conflict point diagram of just a regular intersection. So as you can see here, all the conflict points that we're crossing have been deleted. There's no crossing points. And all the diverging and converging points have been reduced by half. And you can see here that they're a lot smaller. The angles of attack are a lot smaller. So if you had an accident in a roundabout, most likely it'd be a small fender bender or a side swipe, something that's not going to cause as much damage to your car or to the people riding in your vehicle as a T-bone or a head-on collision would. So that's what makes these roundabouts so effective and so much more safe, is that they slow down the traffic and they reduce the amount of conflict points. And as you can see here, everyone is going in a circle so you can see all the traffic moving together. So it makes everyone more aware of what's going on. Some new types of intersections that we're looking at as engineers to implement are the diverging diamond, the single point intersection, and the jug handle, also known as a Michigan left turn. So as you can see in this diverging diamond, it basically gets rid of left turns. So this is in the case of trying to get on an interstate. You would have an on-ramp on this side and an exit ramp on the other side. And once that occurs, you would have lanes cross. So what was now the north-south direction on the right side is now going to be on the left side. So it's almost like now you're driving in Great Britain on the bridge. Then, once you get to the other side, there's a merging lane to get on the interstate. Once that occurs, then you can switch back over to the right side. So, like roundabouts, this can kind of be confusing for people who haven't done it before. But once you have done it and it's been in your town or your city for a long time, it becomes a very useful way and a very safe way of traveling because it gets rid of those left turns. When you have a left turn, you're having to cross 2 or 3 lanes of traffic that are going the opposite direction at high speeds. So this decreases that, and some results and tests have shown in the past when they've used it in states like Missouri and Kansas that it actually creates a safer environment for exiting and entering an interstate. To see the single point intersection, you can click on this link here, or basically what it is it takes the intersection just like this, where you're getting on and off interstate, and combines it to one signalized intersection in the middle of the bridge. So instead of cars coming off, having a stoplight, having to cross the bridge, and having another stoplight, they would all merge to one stoplight. That can reduce the traffic because you have one less light, and now everyone's coming together, and there'll be a lot less left turns too, a lot more through traffic. The jug handle, again, is eliminating left turns. As you can see here, if you're trying to make a left turn in this case, you would have to come off the interstate or the road, make almost a U-turn to go straight through the intersection. In this case, you would have to exit and then cross at a different point, most likely a signalized intersection specifically for people trying to make a left turn. So these are used a lot in states like New Jersey and Michigan for avoiding left turns, and they've also proved successful in the past for creating safe environments. So just to review, today we talked about traffic flow characteristics, what makes up transportation, and how the different vehicles interact. So that was density, volume, congestion, and waves. And we also talked about the signal analysis, the cycle, phase diagrams, and dilemma zones, how we're going to control signalized intersections, how we're going to adjust if one direction has more traffic than the other. And we also talked about safety. How can we as engineers create a safer environment for people on a driving surface? Can we add signs, lighting, rumble strips and stripes, speed control, and in the end we're trying to make forgiving roads so that if there is an accident or some mistakes are made, you're not going to have critical consequences. And finally, we talked about different intersection types. What do we do to consider one intersection type better than the other. We use conflict points. We also talked about roundabouts, diverging diamonds, single point intersections, and jug handles, trying to eliminate left turns, trying to create a safer environment for drivers as they proceed through an intersection.